Hello and welcome to this video in which I will be deriving the dynamical differential equation for the vertical motion of a submarine. I will be doing that based on Newton's second law. Once I complete the derivation, I will actually go through solving the differential equation using SyspI, integrate, and Euler methods, again as I did in my previous video. Now, to start with, again, we need to do some assumptions. And the assumption that are necessary for this derivation is we need to talk about the water density, and we need to assume that the water density is constant. The second is actually the gravity, buoyancy, and water resistance forces that are actually going to be acting on the submarine. And we don't need to consider anything else other than these three forces. Plus the body of the submarine, again as we did with the drone, is actually a rigid body. And we will neglect the pitch roll effect on the submarine to keep the model simple. And also we need to say that water resistance is proportional to the velocity of the submarine. Under these five assumptions, we will now derive our equation. Now, the first thing we need to say that the mass, submerged mass of the submarine is represented by M. The depth of the submarine below water surface is represented by H. The buoyancy force, which is pushing the submarine up, is actually represented by FB, and the gravitational force is Fg, which is acting on the submarine. Now, you need to also understand what do I mean by the buoyancy force, and the buoyancy force is actually equivalent to the density of the water multiplied by the volume of the submarine multiplied by the gravity force. And the gravity force is actually given as F equal to mass times gravity. These are the actual equations which we have. Now we can look at how the total force or the net force is actually made of these separate forces. And we can say that the net force is the difference between the buoyancy force and the gravitational force, which are represented as F net is equal to Fb minus Fg. And if we use Newton's second law, we understand that the force is actually the mass times the acceleration, and we know that the acceleration is the differential of the depth of the submarine in terms of time, so it's represented by d squared h by dt squared, and the resistance is actually given by b multiplied by dh by dt. And therefore, if we substitute all of these different forces, we know that the mass multiplied by the acceleration is equal to mass multiplied by gravity plus the buoyancy force, which is rho multiplied by the volume multiplied by g minus the actual resistance of the water, which is given by b dh by dt. Now, you need to understand what these terms are, and the first term, which is minus mg, is the gravitational force pulling the submarine down, while the buoyancy force, which is rho Vg, is the force pushing the submarine up, and the third term, which is minus b dH by dt, is actually the water resisting opposing the motion. Okay, so now we have all these terms represented in the equation, and we understand what these terms mean. We can dive into solving this equation, because now we understand the equation. We can actually assume some variables and some parameters for our submarine to try and simulate the dynamics of this submarine. So let's not waste any time, and let's dive into our Jupyter notebook. Okay, so as you can see, the first cell in my Jupyter notebook contains the libraries that I will need to solve this differential equation. And I started by importing NumPy and Matplotlib, but if I'm going to use syspy.integrate and the function Odin, then I need to actually bring that also into my Jupyter notebook. So I will run this cell. In the second cell, I have defined my parameters: the mass of the submarine, the gravity force, meters per second square, of course, the density of the water, which is rho, which is known, it's 1000. Then I have the volume of the submarine in meter cubes, which is I defined here as 100, and then the damping coefficient kilograms per second, and I defined it as 500. Next, I actually created my model, which is the submarine model, and I passed to that the time and depth. And then I went and defined my dt to equal h1, and defined the dv by dt to equal minus m multiplied by g plus rho multiplied by the volume multiplied by g minus the resistance, which is b h1, over divided by m, and I needed to return both dH by dt and dV by dt, which is the second and first differential equations. Then I went and initialized the conditions, h to equal 0 and v to equal 0, and then initial conditions are actually both in this case are a series of h0 and v0. Then I created the time array, and I used the function linspace to define the array, and in this case I start from 0 and I stop at 100, and I needed 1000 samples between 0 and 100. Then I actually called the function Odin, and I passed to it the model, and I passed to it the initial condition plus the time array which we have created, and then solved the equation. Then I actually went and plotted my equation, and let's see if we run this what we have. So if I run the first cell, second cell, third cell, fourth cell, and the fifth cell, and you can see that actually I have the simulation of the submarine depth according to the time period which I have defined, which means that even with a little bit of more complicated equations, we should be able to solve our differential equation. It doesn't have, with this Odin function, regardless of how complicated your equation, as long as you can simulate your equation and downgrade it to a first order differential equation, then you should be able to solve it without any problem. And regardless of the number of parameters that you have to pass into your Odin function, you can do it. So it has actually made a complicated equation solution using Python looks very simple. Now we are going to go a step further and see how we are actually going to do the same solution using Euler methods. So again, I started by initializing my creating or introducing my variables and initializing them. Again, the mass is 10,000 kilograms, gravity is the same, rho is the same, the volume is the same, and the damping coefficient is the same. Next, I introduce my time parameters, which are the step is 0.1 and the Tmax is 100. Then I initialize the conditions, and I said that H0 and V0 are actually equivalent to 0, which is the initial depth and initial velocity. Then I created my arrays, and again in this case I am using arange to create the t-value array, which is between 0 and Tmax, and Tmax I defined 100, and dt, which is the actual time step, which is 0.1. So it will give me exactly the same as we have defined it before, between 0 and 100 and 10,000 samples. Then I used NP0 like to create the depth array, and I used like because I passed to this function the previous array, so it can inherit all the attributes of that array, because I want it to be the same data type and the same length and everything. And I did the same with the V array, and then I went and initialized my depth and V arrays as equal to H0 and V0, which are defined in an earlier cell. Then I created a for loop using for I in range, and I used len to actually create the values that we are going to iterate over, and they will be based on the length of our t-value array. Then I actually defined my dh by dt to equal v value I minus 1, and then dv by dt to the equation which we already have, which is minus m multiplied by gravity plus rho, which is the density of water, multiplied by volume multiplied by gravity. And then I have the force of the water opposing force, which is B multiplied by V value, and all and divided by M. And of course, then I wanted to extract the values and multiply them by dH plus dH multiplied by the time, which is 0.01, and which is the time step. And I did the same for the volume for V values, and it's actually exactly the same equation, or the same value, how we extract it and how we update our H value and V value. Next, I used matplotlib to actually plot my results, and I said that I want to plot t value against h value. I defined my x label and y label as time and depth, and then I put a title for my plot, and then I said I wanted a grid around my plot, and then I just wanted to show it in my Jupyter notebook. So let's go and run these and see what we get. So if I run this, first initializing the parameters, and then initializing the arrays and creating them, and then my for loop, which is the Euler method for integration, and the last thing I want to actually plot the result, and as you can see, the result is plotted. Now if you look at this plot here, and if we go and compare that with the plot that we obtained from the solution we did with the ODE function, you can see it's exactly the same solution. So we have managed again to obtain the solution using both methods, which can be very, very useful for comparison. And if you have difficulty solving it in one method, you can apply the other method, and you can see when you're applying the ODE integrating method is much easier than it is to actually go and solve by Euler method, because you have to understand Euler, how to use Euler methods to solve your equation. So I will stop here and I thank you, and I will see you in the next video. Thank you and